Physics as a subject also studies the relationship that exists between physical quantities. That is, studies the mathematical or physical relationship between these quantities. And what are these quantities? Examples are length, time, mass, and so on and so forth. Now, a physical quantity in physics is that property of matter, property of an object that can be measured, that can be calculated, if not being measured with an instrument. You can calculate it using some physical equations that relate these quantities. Now, for example, I'm sure you must have stood on a scale before to measure or to check your mass. Suppose your mass is 60 kg as recorded by the scale. That mass, which is recorded by the scale, is a physical quantity because it's a parameter of an individual that can be measured. How about a car in motion? This car has a speed. The driver may be moving his car at the speed of 50 kilometers per hour, which is always displayed on the speedometer that is on the dashboard. So the speed of that car is a measurable parameter, and it is called a physical quantity in physics. Now, the entire quantities in physics or physical quantities are divided into fundamental and derived. Some of the quantities are fundamental and the rest are derived. And then we have just 7 fundamental quantities in physics. These quantities are also called base quantities. They are base, that is, they cannot be derived by combining any 2 or 3 other quantities. We also call them independent quantities. They do not depend on other quantities for their derivations. That's why they're called base or pure or intrinsic quantities in physics. Again, it is worth noting that every physical quantity must be assigned a numerical value and also a unit attached to it. It's not enough to just mention the mass of a body as 50 and say, okay, I weigh 50. 50 what? We need to specify the unit of measurement of that mass. So we don't use a random number to express a physical quantity. We use a numerical value, a number that carries with it a unit of measurement. Units are chosen standard of measurement of a physical quantity, which has essentially the same nature as that of the quantity that is being measured. For example, the unit of mass is a kilogram, and that of the length is a meter. So when I say the mass of a body is 5 kilogram, this means the mass of that body is the same thing as 5 times 1 kilogram. So which means 5 kilogram is 5 times heavier, is 5 times greater than the unit that is used to define the mass of a body in the SI unit system, which is the kilogram. In other words, you can say that units are standardized values that are used for expressing or comparing physical quantities. We say it's a standard for measuring the same kind of physical quantity. Now, there are different systems of unit. I'm going to measure about 4 of them here. I'll mention 4 systems of unit. We have the FPS. It's an abbreviation for foot, pound, and second. It's a British system of measurement, especially in engineering measurement. It uses foot for distance or length, pounds for mass, and second for time. Then we also have the CGS. CGS stands for centimeter, grams, and second. Centimeter for length, grams for mass, and second for time. Then we have the MKS based on meter, kilogram, and second. It's a system that uses meter as the unit for length, kilogram, unit for mass, and second, unit for time. And then fourthly, we have the International System of Units, simply called SI units. It's a set of units that are globally accepted. They're accepted everywhere. Talk about length, meter in Nigeria. When you get to Ghana and they're talking about length, they also measure meter. They say use meter as the measurement of the length. So this SI unit was introduced far back as early 1960 by the General Conference for Weight and Measure, and it is a modification of the MKS system of units. Now, having said that, let's look at the choice of a standard unit. Now, number one, it should be of suitable size. If I choose kilogram, for instance, and I want my kilogram to be the unit of mass, I must define what kilogram is. They can decide that let this object, of this shape and of this dimension, let the weight or the mass of that object be defined as 1 kilogram. It should be accurately defined. It must not be error there associated with the unit that is chosen. Then it should be easily accessible. That unit, that standard for measurement must be easily accessible. And we should have replicas of it. And these replicas should be available everywhere. Now, the units also should not change over time. It should not change over time. Whatever has been used as a measure of 1 kilogram should remain constant. That material that is used to gauge 1 kilogram should remain the same as long as we want. It should not change over time. And it should not be affected by physical conditions like temperature, like pressure, like humidity, and so on and so forth. Now, let me quickly give you some advantages of SI units. SI units are systems of units assigns only one unit to a particular quantity. For example, the joule is the unit of all forms of energy. But the MKS system, other systems of units can assign calories, for instance, as the unit of heat energy. Number two, SI unit systems follow decimal system. That is, we have what we call multiples and sub-multiples of units. They are expressed as powers of 10. I'll come to that later in my subsequent video. I'll show you how to do this conversion from one multiple or multiples of this unit to the actual unit itself. SI unit system is based on certain fundamental units. That is, before we talk about or derive the units of derived quantities, we have to express them using the base or SI units to obtain them. Now, here are the fundamental quantities we have in physics. There are about 7 of them, and these quantities are also called base quantities because they are independent of other quantities. They are independent of other quantities for their derivations. I have here length, which is the distance or the distance between two points, the length of path. Now, just unit of distance or length is the meter, and then length or distance can be measured in other units such as centimeter, kilometer, millimeter, and so on. The next is the mass of a body, which is the quantity of matter a body has. It is measured in kilograms. That is, the mass of a body is measured in kilogram as the SI unit. Other units include grams. That can also be used to measure the mass of a body. You can also use the centigram, the milligram, and so on. Time. Here we are looking at time as an interval. That is the time during which an event occurs. It is measured in seconds. That is as the SI unit of time. You can also have time in minutes. You can have time in hours. You can have time in days. You can have time in weeks, and so on and so forth. Then the next one is thermodynamics temperature, which is measured in Kelvin as the SI unit. This symbol K is capital. And then we have other units like the degree Celsius can also be used to express other temperature. Can also use degree Fahrenheit to express the temperature of a body. But the SI unit for thermodynamics temperature is the Kelvin. Electric current is the ampere. The ampere, the symbol is A, is the unit of measurement of this fundamental quantity, electric current. And of course, ampere is an agreed unit. It is given in honor of a scientist called ampere. Amount of substance, that is the quantity of matter, is measured in moles. symbol is this. We can talk about a mole of a substance. This time around, we're trying to quantify substance. Substance like water, substance like air, substance like gases, substance like sand. How do you quantify it in physics? We use a mole. A mole of a substance contains as many atoms as 6.02 exponent 23 particles or atoms. Then we have the luminous intensity measured in this unit, candela, CD, the unit of measurement of luminous intensity. So these are the fundamental quantities and their respective units. Okay, before I round up this session, we want to look at the rules for writing the units of physical quantities. Now, number one rule says, the first rule says the full names of units should not begin with a capital letter, that is, an uppercase letter, even if they are named after a scientist. For example, Newton is the unit of force. If I'm going to write this unit in full, it must be written in the lowercase letter, whether it is the first letter or any other letter of the word Newton. Of course, this rule contradicts what we learned in English language, that the name of a person is a proper noun. So it should begin with a capital letter, but not so in physics. Except you are writing it, maybe you want to use the symbol for Newton, then it must be in capital letter, in the uppercase letter. But if you must write the name in full, you must use the entire, you must use the lowercase letter. The same applies to units like watt, like ampere, like meter. Okay, the second rule is that there is no plural form for units. For example, 10 kilogram is not 10 kilograms. It's not the same thing as if you write it this way, it means something else. We are saying here it is 10 kilograms second because we interpret this as second. So no plural form for units. Number three, if the symbol of units that expresses the name of a scientist is to be written, it must appear in the uppercase letter. I've said that before. Okay, so these are three rules. Then the fourth rule is that within or at the end of symbols representing units, no full stop is required. So we don't need to apply or place or put any full stop or comma after the unit is written. So this is wrong. This full stop is not supposed to be here. We don't need any punctuation mark here. Then the fifth one says there should be a space between the number and the units. An example of stating the mass of the body as 5 kilograms, there should be this space between 5 and the kg, not this. So these are the rules for writing units of physical quantities. The next video will look at derived quantities and how to derive their units.